Okay, so let's start. We have to cover a lot. So my name is Rajal Mukherjee, and I'll be taking this live session for NPTEL course on computer organization and architecture. I'm a research scholar at IIT Kharagpur. And this session will generally we will be solving problems like every week. On this, on the on the course that has been covered for week like this week 9. So the questions will be similar to that asked in the assignments, and let's start solving them one by one. So this is the first question. Consider a hard disk that is rotating with a speed of 950 rpm. The maximum rotational delay or latency will be how many milliseconds? Right. So I hope everyone has a little bit idea of what that how the hard disk works and everything that has been covered in this week's class. So let's start it well a little bit. So the question says the disk makes 9500 revolutions in 60 seconds, right? So it says the what is the maximum rotational delay. So that is measured as like this, like for one rotation what will be the time consumed. So we can, from the statement we can derive like this. So for one rotation, time required will be 60 divided by 9500 seconds, right? So this basically summarizes what is the term that is given here is maximum rotational delay or latency. So this gives the the time consumed for one rotation basically gives the what is the maximum delay or latency. So if we calculate this, it will come down to it's in seconds, so let's simplify it a little bit. 60 into 100,000 divided by 9500 milliseconds, that will come down to 6.135 milliseconds. So that is the time required. That is what we define as maximum rotation latency. Right. So so any doubt regarding this? What is 8.7? I don't think that is the answer. This is the answer. So any doubt regarding this? Okay, so let's go to the next question. The question is, which of the following memory devices cannot be used for backup or as a secondary storage? So the options given are DRAM, SRAM, floppy disk, hard disk, and flash memory. So which will be the answer of this? So we all know DRAM and SRAM are volatile memories. So what happens is they retain data as long there is power supply. So if you have like in the previous lectures you have seen that DRAM and SRAM are composed basically of transistors. So DRAM is used, SRAM is used for cache, and DRAM is used for your main memory. And this like floppy disk hard disk floppy disk, hard disk, and flash memory are basically magnetic devices, and they store the data even when there is no like these are the generally sort of memories that are used for storing data as a backup. So the correct answer in this case will be uh, C. Sorry, this cannot be right. So the correct answer in this will be A and B. So they cannot hold. These devices cannot be used for storing data for backup. Okay, so and these are basic questions like that will be asked, and these are very scoring ones. So let's go to the next question. The question is, which of the following statements are true for hard disk? It is faster than solid state drives. Sector is the smallest unit of data transfer. It does not have any moving parts. So let's revise what is a hard disk. So hard disk consists of basically platters. So these are we call platters. So each hard disk consists of platters. The platters in turn consist of uh, like tracks. These are circling tracks. So the platter consists of tracks, each platter. So each platter has basically two sides. one at the top and another at the bottom. So each side has basically tracks. Now what is this sector? So each track is further divided into sectors. So sector is the smallest unit of a hard disk. So what we discussed, one is platters. In the next level we have tracks. In the third level we have sectors, right? Now now the question says, um, we like which of the following statement are true for hard disk? A, is it faster than solid state drives? No, hard disks are not faster than your solid state drives. They are comparatively slower than your uh, than your um, than the solid state devices. So option A is false. No, option B, sector is the smallest unit of data transfer. Yes, it is true. We have just now discussed sector is the smallest unit. Hard disk is divided into platters. Platters are divided into tracks, and tracks are divided into sectors. Option B is true. Option C, it does not have any moving parts. No, it has moving parts. Each of the disks are basically rotating, and there is a head which basically we need to point it to that. Like when we have to read a sector, we have to point the head to that sector because it is rotating in this case. So this is false. And option D, it is volatile in nature. It is false. It is basically non-volatile in nature. That is the reason it is used to store data, right? So the correct answer is B. Any doubt regarding this? If you have any doubt, you can ask. We will discuss it. Okay, so let's go to the next question. So this is a very typical questions that are asked for this hard disk type, hard disk type problems. Like in this, you will giving either to calculate what is the total capacity of that disk, or there is another type of problem where you have given like to calculate what is the data transfer rate. So this is one of a kind sample problem that is very common and asked in most of the competitive exams also. The question says, consider a hard disk with two double-sided platters, 2500 tracks per surface, 200 sectors per track, and the sector size of 1024 bytes. So what is the total capacity of the disk it will be in like how many gigabytes? So let's define something. Like it is given the sector size is so it is given the sector size is 1024 bytes, basically 1 KB, right? Now first we need to calculate bytes per track, like how many bytes it's stored in each track. Now it says each track has 200 sectors and size of each sector is 1024 bytes, that is 1 KB. So that is 200 into 1 KB, that is 200 KB, that is 1 bytes per track. Next we go to the next, uh, like the next part, that is bytes per surface. You see each it is given you see it is given there are 2500 tracks per surface, right? So like there are 2500 tracks. Now we know what is the number of bytes per track, this, so we need to multiply it by the number of tracks. So 2000, like how many number of, what are the number of surfaces we have, number of tracks per surface, 2500 into 200 KB, right? That is the total bytes for each surface. Therefore it will come down to 50 50 0000 KB, right? Now we will find the total capacity. So what is given? It has two platters, like the hard disk has two platters, right? So there will be two, and it also says it is double-sided platters. That means both the surfaces, like there is a disk, the, like if this is one disk, so this side and the down below side both are the places where data can be stored. So into 2 into 50000 KB. So this will come down to 4 into 50000 KB, that is 20 KB. That means that is 2 GB. So it comes out to be 2 GB, right? So the correct answer is 2 GB. So any doubt regarding this? So first, I will again repeat. So this is a very typical problem which will be provided to you lots of time. So first thing you need to see the question. The question says there is a hard disk. Like I have drawn the hard disk in the previous question. So this is the hard disk. Hard disk has platters. Each platter has tracks, and each track has the minimum unit is sector. So there is platter, there is tracks, there is sector. So here the question says we have a hard disk with two double-sided platters. So that means each platter, in both the sides data can be written, and there are two platters. So there are how many surfaces? 4 surfaces, 2 into 2. Next it says there are 250 tracks per surface, 2500 tracks per surface, 2500 tracks per surface, and there are 200 sectors per track, 200 sectors per track. Then it is given what is the sector size of 1024 bytes. So this is the sector size. First we calculate how many bytes So sector is the smallest unit. Next we need to, so first we find the number of bytes each for each track, that is comes down to 200 kb. Then we calculate number of bytes per surface, that comes down to the 2500 surfaces into bytes of each surface, each track. So this is the number of tracks and size of each track. This come to the size of each surface. Total capacity is 2 into 2 because each for like there are each platter has two surface and there are two platters. So 2 into 2 4 into 5. This value, it's come down to 2 GB. Clear it is. If you have any doubt, you can ask. Okay, so let's go to the next question. And this is another typical question that I was talking about. So question says, consider a typical disk that rotates at 1500 rotations per minute and has a transfer rate of 50 into 10 to the power 6 bytes per second. If the average seek time of the disk is twice the average rotational delay and the controller transfer time is 10 times the disk transfer time, the average time in milliseconds to read or write a 500 byte sector of data. Now let's discuss the various time that is that is part of this thing called disk access time or disk transfer time, whatever they say here. So the term is sometimes called disk latency or disk access time. It consists of generally three parts. One is seek time, one is rotational delay, and the other is transfer time, data transfer time. Right. So what is seek time? Seek time is the time required to move the head of the move the head to the desired track. So as we have mentioned, there are there are circumcircles of tracks in each surface of the disk. So the time required to move the disk from one track to another track, that is the seek time. So it depends on the track. So the next is rotational delay. So once so suppose first we reach the again let's use that diagram. So there is sector, there is track. So first we need the head to reach to a track. Once we reach the track, what we need to find the sector from where we need to read the data, right? So that depends on the rotational delay. So once we reach that sector, then the time required to transfer the data, right? Right. So this is the third variable. So these are the three things that is required for disk latency or disk access time, right? Occasionally here it is given that controller transfer time, that is very, sometimes it says it is present, sometimes it's basically a overhead we can consider. So that is basically seek time plus rotational delay I mean, I cannot increase it. Like you can increase your browser's like zoom in thing. You can increase that. That you can do for like viewing the question. That is very easier. Plus rotational delay plus data transfer time plus controller overhead. So these are all the variables that are required to calculate the disk latency or the disk access time. These are the same type of terminology that is used. Okay, so let's solve this problem. So it says we have a typical disk that rotates at 1500 rotations per minute and and has a transfer rate this. So it is given. So first you need to find out like there are few things given that we need to find, that is average rotational delay. That is basically average rotational delay is 0.5 divided by, it is given, it is making 1500 rotations per minute. That is 1500 divided by 60. So this will give us the like average rotational delay. So if we calculate this, it will come down to 2 milliseconds. Next, it is given the seek time. The average seek time of the disk is twice the average rotational delay. So seek time is twice the average rotational delay. Basically 2 into 2, 4 milliseconds, right? Now next it is, we need to find out the transfer rate is given. What is the transfer time required? Transfer time is basically the time that is required to transfer this 500, see it is given 502 byte sector of the disk, and this is the rate. So it will be 512 divided by 50 into 10 to the power of 6. So if we calculate this, it will come out to be 10.24 microseconds. Next, it is given the controller overhead. The controller overhead is 10 times this value. Into 10.24 microseconds, that will come out to 0.1 ms. Okay, so total time total like disk latency is seek time plus rotational delay plus transfer time plus overhead. So if you look, the seek time was 4 milliseconds, rotational delay was 2 milliseconds, transfer time was 10 for 2 microseconds, plus overhead was 0.1 ms. So it will come down to 6.1 ms. Yeah, I will start from fresh 1 second. Don't worry, I will again. Yeah, so let's start again. And so there is disk latency. So there is disk latency. The disk latency consists of seek time, rotational delay, and data transfer time. So if you have looked at this diagram, so the diagram consists of platters. Then there is, each platter has tracks, and there is sectors, right? So each platter consists of a circumcircle of tracks, like many tracks, and the smaller data unit is sector. So how does the how to read data from this setup? So first you need to reach there is a overhead, there is a head, so that rotating head first sets it on the track. Then from the track we need to get to a particular sector from where the data has to be read, right? So there are, these are the things that are there. Then this first is the seek time. The seek time is the time required to put the head onto the particular track, that is the seek time. Then there is the rotational delay. Rotational delay occurs because we need to reach to a particular sector in that track. Then is the data transfer time, that is the amount of data that you need to transfer. So in this question, if you see, we have to transfer 512 by sector of data, and the transfer rate is given as 10 into 10 into 15 to 10 to the power 6 bytes per seconds. So this latency is actually given as seek time plus rotational delay plus the data transfer time and some overhead. It's generally mentioned in the, it is already always given in the question if there is any overhead or not, but generally there is very few overhead, it is not given, and it depends on the different kinds of overhead. So here it is given as controller overhead. So that is the data access time. Now what is the average rotational delay? Average rotational delay is given as half that of the, how much time is the rotational how much time is required for half rotation. So if you see, the rotational speed, the speed is given as 150 rotation per minute. So if you go to the question number 1, we have calculated this, how to find rotational delay given a rotating speed. What we did, we divided it 60 by 9500. Yeah, you can ask. One minute. Yeah, you can ask now. Yeah, so this is how the rotational delay we calculated. So similar way we calculated it in this question, that is 1500 divided by 6, and it is always average rotational delay. So average rotational delay is basically half of the rotational delay. So in this case it will come down to 2 uh, uh, 2 milliseconds. Next is the seek time. Seek time is basically, here it is given as twice the average rotational delay. It is mentioned here. Average seek time is basically twice the average rotational delay. So that is 2 into 2 milliseconds. That is 4 milliseconds. Next we have to like find the like transfer time, data transfer time. Data transfer time is basically the data and the amount of at the rate at which it is being transferred. That is 50 into 10 to the power 6 bytes per second. So it's come down to 512 divided by 50 into 10 to the power of 6. So if we calculate this, it will come down to 10 into 2 to the power 10.24 microseconds. Next, there is the controller overhead. That is 10 times it is given as that controller overhead is 10 times the disk transfer time. So that is 10 into 10 to the power of 10.24 microseconds. That will come down to 0.1 milliseconds. So these are the values we need to consider. So the total disk latency is seek time plus rotational delay plus transfer time plus overhead. So that comes down to 4 milliseconds plus 2 milliseconds. This one is 10.24 microseconds and 0.1 milliseconds. So it is come down to 0.61 milliseconds. This is from next week. I will do it next week. You ask me, I will do it next week. Programmed IO is from next week. So we will discuss those problems next week. Yeah, I've given in the mic. You can ask Mughal. So this question they have given for this week's assignment. Programmed IO is not in this week's, right? Programmed IO is from next week. Isn't program IO next week? Week 10? And if it is given it assignment, then I learn, then I can't solve it. Like no, then like I can just give you a hint. Then other than that, I cannot give you much of a details. Suppose we want to read 500 data in programmed IO where the bus width is 16-bit. Each time an interrupt occurs, it takes 10 microseconds to service it. That is transfer bit. The CPU time required to read 500 bits of data is CPU time required to read 500 bits, 5000 bits in. So you know what like how programmed IO transfer occurs, right? So what you need to do is each time an interrupt occurs, it takes 10 microseconds to service it, right? So how many interrupt occurs in a programmed IO where the bus width is this? So you need to think like that. So every time you need to add the data, like you are reading 500 bits, okay, that has a transfer rate, now for each, if you check that interrupt occurs, 10 microsecond is required to service it, that is transfer of 16 bit data is like 10 microsecond is required to transfer that data. So that 10 microseconds you need to each at time a programmed IO based interrupt occurs. That way you need to do it. There is a normal transfer rate, and then there is the that programmed IO transfer rate, like in a altogether. Okay, so let's go to the next question. The question is, which of the following is are true for IO mapped device interfacing? Separate address decoder is used to select memory and IO ports. Some of the memory address space is occupied by IO devices, and same instructions for memory and IO operations. And the last one is like all of this. So we know what is an like IO mapped interface device. So basically there are separate address space for IO and memory. So there there is a memory address space, then there is the IO address space. So in IO map devices, we may so if you check, the option A is correct, because since there are separate address space for IO and memory, we need separate address decoder to select the memory and the IO ports. So option A is correct. Option B says some of the memory address space is occupied by the IO devices. No. So this is IO and this is memory. So both are separate entity. Both are different address space. Same instructions for memory and IO operations. Again, both are separate entity, separate instructions. So false. So the correct option is option A. So next question. The question is, assume we are executing some programs P1. During the execution, some interrupts are generated which are listed. Mark the instruction types which allow the instruction being executed to be completed before handling it. One is timer interrupt, one is page fault interrupt, C is IO interrupt, and D is all of the above. So the thing is, one, so there are quite a bit distinctions between a page fault interrupt and a timer and IO interrupt. So in case of timer an IO interrupt, like they are handled generally after finishing execution of P1. That is the program. But what is page fault? Page fault is your page fault is basically you are executing you are executing P1, but some amount of the data that is not currently present in the memory, it is being requested. So that is at that point you need to handle that interrupt. Otherwise, it is not you cannot proceed for like for that for the execution of the program. So A and B can like A and C can continue and they will be addressed after the instruction is completed, but when B occurs, that is in case of page fault, it has to be like delivered at that point only. So you know what is page, right? Or so you know what is page, right? So like each when a program is being executed, it is basically divided into like smaller units called page. So at a point of time, all the pages are not loaded in the memory, only small amount of pages are loaded in the memory. So when a page fault occurs, it means the program that will be executed requires a page that is not currently present in the memory. We need to get it, and so at that point
Handled after then what, right? Handled after then here, right? What?
yeah. So what happens when there is a page fault? Page fault happens, that means at that point of time the particular page is not present in the memory, so we need to access it from the it is not present in the RAM, and we need to access it from the secondary memory. So at that point, that fault has to be delivered, so that interrupt has to be delivered at that point of time. So that's why it is different from that of an timer and IO. So what happens in case of a timer and IO? The program basically goes to sleep, and whenever that timer and IO operation is completed, then it comes back. So the correct answer is here A and C. Those are the instructions that allow the instruction to be completed before handling the interrupt. Okay, so let's go to the next question. So which of the following statements are true for data transfer technique? Interrupt event technique transfers data faster than DMA mode of transfer. Asynchronous data transfer can be used for high speed devices. Interrupt event data transfer waste more CPU time than asynchronous data transfer. Option D, none of the above. So let's check one of them one by one. Interrupt driven data technique transfer is faster than DMA mode. False. DMA is faster. So DMA is false. DMA is the fastest mode of data transfer. Let's come to option B. Option B says asynchronous data transfer can be used for high speed devices. False. Asynchronous means one after like data cannot asynchronous means that data are not synchronized. That kind of data transfer are used for high speed devices. That is false. Synchronous synchronous is used for high speed devices. Option C, interrupt driven transfer waste more time than than asynchronous data transfer. No, asynchronous interrupt driven is faster than asynchronous. So correct is none of the above. All of them are false. So let's come to the last question. The synchronous data transfer can be used for keyboard. So it is no. So this is because synchronous data transfer mode allows data transfer at fixed speed, right? But the end user who is typing the keyboard, that means at that place what will happen, that his or her speed will be limited. Either he cannot go at a speed higher than that or lower than that. So he has to maintain that same speed. So that a result that is not suitable for keyboard typing. So the correct answer is option B. Yeah, eighth I will explain once again. So here it is given that which of the following statements are true or false. So interrupt driven technique transfers data faster than DMA mode of data transfer. False. So DMA is the fastest. As you know, in what happens in case of DMA. In case of DMA, the functioning of the data transfer is the control is given up from the CPU to the DMA controller. So that's why it is faster. So once the data transfer is completed between the input output device and the DMA controller, then the DMA controller sends a signal, okay, data has been now transferred, and in the meantime CPU does lots of other work. So what happens in interrupt driven? In interrupt driven, it is said that like once interrupt is done, then it has to do a check that whether all the interrupts has been completed, and you need to keep a loop that whether the interrupt has been served or not. So that's why interrupt driven is slower than DMA mode. So DMA is the fastest. So next it is given asynchronous data transfer can be used for high speed devices. No, high speed devices, it is false. Synchronous data is used for high speed devices because those are fixed data speed. Next, now option C. Option C says interrupt driven data transfer waste more CPU time than asynchronous data transfer. No, interrupt driven data transfer waste less CPU time than asynchronous data transfer, where one data is being served, then again another is served. So all of them are false. Correct option is option D. So now it is clear. Okay, so this was the last question. If you have any doubt, you can ask regarding any of the questions that has been discussed. So I will say these two are the most important questions. This question 5, which I have discussed, and question 4. Like these are the common type of questions that you'll find in any competitive exams like GATE, or if you are preparing for some exams. These are the most common type of questions. So please try to do this one, like practice this type of problems more. This question 4 and question 5, like it will help you a lot. Okay, then we will meet next week. We'll meet next week at same time.